How's everybody's weekend? Good weekend?
So far, so good.
Anybody do anything fun?
No, I explicitly did nothing fun.
Sure. Me neither.
I drove 15 hours to Dallas. My sister was moving there, so I had to drive her there.
Nice.
Uh,
Nice. What's she moving there for?
she's transferring there, and just trying to start her life out there. So I think from Wednesday at 5 p.m. started driving from Tucson, drove through a rainstorm in New Mexico, then finally made it there at like 8 in the morning.
Right. All right, it's 9:45. Let's get started. Lord, thank you for bringing us together this morning. Thank you for all the blessings that you've given us. I pray that you would continue to help us to get through the rest of the online portion of this semester. Help us to stay focused. Help us to get everything done that we need to. In your name we pray. Amen. All right. So week 2, right? We're in week 2. We've got some stuff to talk about. You guys had a lab due on Wednesday. That's a thing, right? We'll talk a little bit about that tangentially today, not directly. You'll see what I'm talking about. All right? You guys hopefully can see this here. Let me see something here. Yep, that's fine. Okay, so preload. Brian, Thanos is dead. All right, so preload. Since we'll go with preload, let's talk about preload. So in certain systems, you will have preload, right? What is this? Well, the easiest way to visualize this, right? The easiest way to visualize preload is the exact system that we're using. You've got a spring hanging from the ceiling with some mass attached to it, right? Because the mass isn't plummeting towards the ground, right? You have enough preload in that system to hold it up, right? It's in static equilibrium. Certain systems, we want a certain condition to be met, right? So, for example, like shocks in your car, right, have a certain preload on them. Other mechanical systems sometimes have them, right? You'll see like things need to be torqued. We need to torque screws to a certain preload, right, to resist torques that we would have, right? So certain systems, you want that little bit of extra force in there to start with. But what we saw, the main point of that one problem in class last time was that if we are in fact starting from an equilibrium position, the effect of the weight of the object doesn't matter, right? Because it's already accounted for and will cancel out, right? So it's not something that we need to really worry about. Okay. Everything else on there was just tangential stuff. You guys have any questions from over the weekend that you come up with based on last lecture or anything you want to talk about? Because we've got quite a bit to do, right? And then we're going to do some examples today too. As a note, right, I didn't want to scare you guys with the week 2 examples. That's not my intent. I just want you guys to try them and do as best as you can. Really what you should be striving to do at this point is really setting up the free body diagrams, right? That's really where we should be at, right? I don't want you to feel like you're a failure if you couldn't do the problem start to finish, but I did want you to try on those. And we're going to do some of those in class this week. All right, pendulum lab due tomorrow night by midnight, homework 1 due on Sunday. All right, let's do it. So let's talk about today rotational mechanical systems. Then we'll talk about parallel and series elements. We'll do a little bit with nonlinearities, and then we're going to do some problems. Okay. So I said it last class, and I'll say it again, right? The difference between a rotational mechanical system and a translational mechanical system is physical in nature, right? One translates, right? One translates and one rotates. I'm not going to do it all the way. It's my coffee, and if I don't have my coffee, then we're going to have problems, right? So we still have these elements, right? We've got inertia, we've got damping, and we've got stiffness still. They're just rotational, right? So what is the difference, right? Well, we just went over it. It's purely physical, right? From a mathematical standpoint, the only thing that you are changing is the variables, right? Instead of distance, right, you have an angle. Instead of a velocity, you have an angular velocity, and instead of acceleration, you have angular acceleration, right? Purely rotational systems do in fact exist in the real world, right? Like a windmill is a purely rotational system, right? It spins on a fixed axis. These are called rotation about a fixed axis, right? When something rotates and translates at the same time, that is what we consider to be general plane motion, right? And for rigid bodies, this can get complex in certain cases, right? So how do we handle purely rotational systems or just rotational mechanical systems in general, right? Well, we do translational systems. We're going to start with a free body diagram of each inertia, right? And each inertia results in a second order ordinary differential equation. Right? So let's do by example here, right? Let's take a look at this. All right, so I've got a toroidal segment piston, J1, that is matched with a toroidal segment cylinder, J2. Right, so my pistons on the left, my cylinders on the right, both have inertia and both can rotate, right? There's some torsional spring connecting the two together, and you can see that we've got some viscous friction on the edge there, right? And we can assume that that's all the way around, but between the ground and the inertia, right? A diesel engine provides an external torque T in of T that appears as equal and opposite pairs on both this. So imagine for a second, right, that this is my, sorry, move this a little bit. Imagine for a second that this is my toroidal segment cylinder, and I'll angle it a little bit. It's getting torqued equally and oppositely on both ends, okay? Like that. Great. So what do? Right? We want the positive angular displacements measured clockwise from the untwisted equilibrium positions, right? So let's make a model, right? How do we start? Well, we got a free body diagram, right? So what's our free body diagram look like for something like this? Now there's two ways that we can do this, and I'm fine with either way, right? And you can choose, right? But we need one for each mass, right? I'm not going to do an inertial diagram for this. I'm not. We're just going to focus on the FBD for this right now. So I've got J1 and J2, right? I'm going to have some coordinate system. I'm going to use Cartesian for this in particular. And we're going to say that this is theta 1, right? And this is theta 2. This is theta 2 in that direction. All right. So the easy one to put on there, right, is we're going to put on our input torque, right? And our input torque is on each, and it's an equal and opposite pair. And where did we get that from? Well, let's go back here, right? We'll go back one. So if I go back here, right, we can see all I've done is basically turn this so that I'm looking at it head on, and I'm drawing these things as circles, right? Or as near to circular as I can do freehand. And so all I've done is imagine you rotate this 90 degrees and now you're looking at it face on, right? Okay. And so now I've got one torque going counterclockwise, right? And one going clockwise. Now you'll notice that I changed the sign of these, right? And the reason I did that is because, well, positive is the other way. Does it matter? No, it doesn't matter. You can do it however you like. It does not matter. As long as you are consistent with your signs, everything should come out, right? So let's talk about this then, right? So we've got damping on these, right? We've got damping. We'll talk about the damping first. So that damping torque, right? It's going to be a damping torque here. It's purely rotational. Is going to be here, T sub B. Okay. All right, well, that's T sub B. Interesting. Notice it is going in the opposite direction of my motion, right? It has nothing to do, right? It has nothing to do with the fact that this torque is opposing it. We are concerned only with how this moves with regard to theta 1, right? Because our friction is going to fight our displacement. Right? Our friction is going to fight our displacement, which means that it's going to be not intuitively in this direction on the back half of the system. Okay. And now we've got spring. We've got this spring in here, right? All right, so if I'm twisting this, right, I'm twisting this and we're creating separation forces in that direction, right? Okay. So what's going on with this spring? Well, I am going to assume that the spring fights the motion on this side. However, because it's connected, it has to be equal and opposite on the other disc. Could you have chosen TB to be the other way on the other disc? Yeah, if you wanted to choose that it was moving in that direction, you could. That's fine. It's just going to change your signs, right? So just be consistent with your signs. I prefer to do everything with a positive sense of motion, right? Because then if it comes out negative, I know that I chose the wrong way and it goes the other way. But you can do it however you like, right? All right, so I told you there's two ways to do this free body diagram, right? But before we get to the next way, is everybody okay with this? You have any questions on how I got this free body diagram? No? Nothing? Everybody's all right? Okay. Well, all right then. So far, so good. So what's the other way I can do this free body diagram, right? And again, you can do this however you like. Hopefully I have an extra free body diagram slide in here. That'd be sweet if I did. Yeah, I did. Okay. So what's the other way I can do this? Well, what if I wanted to draw this almost like my translational system, right? Where instead of drawing it as rotations, because I'm not so good with rotations, right? Things start to spin and I start to get sick. I'm much better with things just translating, right? So let's pretend for a second that this is a translational system. How do I get this analogy to work out, right? Well, that, right? I would have some input torque in. I'm sorry, that I drew that in the wrong direction. It should be positive. Some input torque in here, and I'm pulling on the other one with the same torque in the other direction. Okay. Well, I'm going to fight my motion here. It's not B1, it's just TB. And I will also have TB here. And then I've got my springs, T sub K and T sub K. Is it required for you to have to do this multiple ways? No. But if you prefer thinking about it like this, then do it like this. If you like the rotational version of it better, do the rotational version. The thing that you need to remember when looking at this is that these are torques still, right? We've essentially created a translational system that is analogous to our rotational system via this drawing, right? So make sure that you're looking at your positive and negative and drawing your torques correctly as forces, right? Any questions so far? Any questions so far?
Is the methods, like you're talking about how we can choose to either do one or the other, but is it like situational, like one might be better to create than if we were to do rotational, and it'd be better to do this way?
It all depends, Carl, on how your brain works and how you like to visualize things. There's no, so if you find this to be more appealing than this, then do it the other way. Personally, I like this because it helps me to remember that things are in fact rotating. But you know, this is just as valid, right? As long as I put my coordinate system on it. Right? So it works just as well. You'll get the same equations when you sum the torques. So obviously that's what makes it equivalent. So it's up to you. It's up to you. Question. Any other questions? Okay. So let's move on to the next part, right? Which is inputs and outputs. All right. So what do you guys think my input is on here? If you had to guess, let's throw out a wild one. What's my input? Guys, not even Monday morning, guys. It's Tuesday. Come on.
Torque in.
Yes, thank you. It says it on there, right? It says in. Torque in is a function of time. Scott. What are my outputs or my output? Is there more than one output? Kind of gave it away. There is. So what are my outputs?
Both the angles.
The angles, yes, exactly. Right. So I put in some torque and I get some movement, right? I get theta 1 and theta 2. Remember, these are cause and effect relationships, right? So I did something and so I'm expecting something to happen, right? What is it? More often than not, for mechanical systems, right, we put in a force or a torque and we get out some change in position or velocity, right? Those are the typical ones that we're going to be looking at. When we get to electrical systems next week, things will change, right? Because you shouldn't be getting a velocity. Well, that's not entirely true. You can get a velocity out of electrical mechanical systems. But, all right, before I confuse everybody, right? We're good on inputs and outputs, right? So what does this mean for me, right? Well, this means that I want everything in my equation to be in terms of these variables, right? And because I have two masses, two inertias, right? Because I have two inertias, I need to write an equation for each one, right? But we'll get there in a second because we'll start with our general mathematical truths, right? Well, it's a rotational system. So I've got some of my torques is equal to J theta double dot. I do have damping, so that's going to be B theta dot. And I've got T sub K, which is going to be K. And remember, that's the rotational spring constant. And the way that I've drawn this, right, I've drawn this how? It's going to want to come back. So let's go back up to our, right, so I've drawn this. If I look at this one, right, I've drawn this spring in what? Compression or in tension?
Compression.
I heard a compression. Is it compression? The spring
I
force
thought
is
it's tension because it's pulling out, so it's tension on the spring.
yes, Carl, that's correct, right? It is in tension, right? Because if you're going to pull it apart, then the spring force is going to want to pull it back in. Remember, it's a reaction force, right? It's not an applied force, right? The spring wants to react to how we're pulling it, right? So this is drawn in tension, right? And because we're drawn in tension, how does this system get to be in tension, right? Well, remember, I have mine moving in the opposite way, right? So let's just do this to really express that, right? So if this is going to be in tension, that means what? That means that theta 1 has to move more than theta 2, right? Think of it this way, right? If you had two cars that were attached by a spring, the only way you would get in tension is if the lead car moved more than the rear car, right? Because it would extend the spring. So this front one has to have more rotation than the back one based on the way that I've drawn this. Is it wrong to do it the other way? No, it's not, right? You're just going to be in compression instead, and it's going to flip your signs, and it'll all take care of itself in the math, right? But this is in tension, and because it's in tension, our mathematical truth becomes theta 1 minus theta 2, right? Because it is a free-ended spring, right? The spring is allowed to move on both sides. And that's it. Those are the truths, right? That's that. We've got right. We've got our mathematical truths. We've got our free body diagram. We should have everything we need to start piecing this together, right, and do our reduction of equations. So let's do that. And the way that I'm going to do it is I'm going to start with the first inertia J1. Right. So if I can get the mouse to work, there we go. Maybe there we go. All right. So for the first inertia, right, for J1, well, what do I have? Right. Well, my torques are Tn. Right. Then I've got negative Tb minus Tk is equal to J1 theta double dot. Okay. So all I've done is I said, look, there are my applied torques, right? From the free body diagram, I know the sense of them, whether they're positive or negative, and that all has to be equal to my inertial term, which for a rotational system is the inertia times the angular acceleration. Okay. Then we can plug in the rest of our truths, right? Minus b theta dot 1 minus k theta 1 minus theta 2 is equal to J1 theta double dot. And we're almost there, right? We just have to get all of our inputs on one side and all of our outputs on the other. In this case, the only input that we have is Tn, right? So we can isolate Tn on one side. And then our outputs are theta 1 and theta 2, right? So J1 theta double dot 1 minus b theta dot 1 plus b theta dot 1 plus k times theta 1 minus theta equal to T. And I'm going to stop, and I'm going to call that equation 1, right? This is my first equation, right? Awesome. We are halfway there, right? Halfway through the reduction process. Okay. So now we rinse and repeat for J2, right? That's where we're going to go. Could you, if you wanted to, write this term out, right? The multiply out k theta 1 minus k theta 2, sure, doesn't matter. Not for right now. There will come a time when we are going to want to multiply that out when we get to Laplace transforms, but that's in a few weeks. For right now, if you just left it like this, like on a quiz on an exam or a homework, right? That would be sufficient. Yeah, that would be sufficient. All right. So let's talk about J2 then, right? For J2. And for J2, if I sum my torque, so I'll have negative Tn minus Tb plus Tk is equal to J2 theta double dot 2. Okay. And I can plug in my truths again, but this time it's B theta dot 2 because it's only, right, this is not a, remember, there's the friction is on each of the halves, right? So one is dependent just on theta 2 and the other side is just on theta 1. They're not connected together. Plus K times theta 1 minus theta 2. Now, you'll see something kind of interesting here, right? Kind of. I want you to notice something, right? Look, when I bring this, because we're gonna bring this over, right? We're gonna manipulate this and leave Tn on one side and everything else on the other, right? Because inputs on one side, outputs on the other. Right, so look, right, I'll get plus B theta dot 2, right, minus K theta 1 minus theta 2, right, is equal to negative Tn. Now the thing here, right, is if you did the algebra, you'd get plus K theta 2, right? Getting your equation to come out as, you know, theta double dot plus theta is pretty standard, and it's a good tell as to whether or not you did it correctly. There's a reason. Right? There's a reason. We kind of will touch on this later, but not in much depth. But you guys may have heard of the Ruth Hurwitz stability criteria, which says that if the sign of each of the right, so if the sign of theta double dot, theta dot, and theta are all the same, then you have stability. If they're not, then you'll be unstable. But for now, sufficient to just leave it like this, right? Boom, we're done. It's the model. The model is the two equations, one for each. Now, what order system is this? You guys have gut feeling. What do you think? What is
Second order system.
Part of the way there, Danny. Is it just the second order system? This particular,
I suppose the third order system.
this particular piece is second order, but you've got two second order systems, which makes the entire system fourth order.
Right.
All right. It's described by two second order differential equations. Another way of thinking about this is if you were to create one master equation, which we'll talk about this one characteristic equation, we'll talk about it with Laplace transforms. You'd end up with a fourth order characteristic equation, which would require 4 roots to solve, which means, you know, that you've got stability from 4 different roots that you need to consider. Does have any other questions? Right, we are not going to do this. We're not going to do the next step, right? We're not going to evaluate. We're not there yet. But do you guys have any questions for this? Is everybody following? Everybody doing all right? Maybe. Okay.
I have a quick question.
Yes.
What's the difference between the double dot and the single dot? Like, I know, like, it's, I don't know, it's just a little confusing.
Right. So theta double dot is the time derivative of theta dot which is the second derivative of theta. Okay. So each time you have the dot, that means you took the time derivative, right? So
Okay.
theta double dot is equivalent to alpha, which is our angular acceleration, where theta dot is omega, which is our angular velocity. Sometimes books use primes, right? But prime does not, the dot is special. The dot means that there's time dependence. The prime just means that you're changing with respect to some other variable. That's why we're using the dot. The dot is specific to a time derivative. It's specific to that. All right, so I noted this, right? So this one, I believe that there's one like this in your text, right? As an example, my equations are going to look different because I chose a different coordinate system, right? They are both valid, so just be aware. Okay. Any other questions? Everybody doing okay? Following? All right, let's talk about parallel and series springs, right? So sometimes, it turns out, kind of like when you have a circuit, you can have mechanical elements that are in parallel or in series, right? You can have multiple. All right, so what's a real world example of this, right? Anybody who has an automatic garage door, right? Your garage door has a spring on it, right? In some configurations, they will put two springs on it in parallel, right? Because it helps to distribute the load. So that's a real world application, right? Another thing is when you have, how many people here have seen the movie The Goonies? Okay, good. So all, most of your parents didn't fail you completely. So in that movie, they're doing the guy, Josh Brolin's character, Brendan, is doing the chest exercises, right, with the spring thing, and they wrap them up with it, right? Those are springs in parallel, right? So some workout equipment actually uses this stuff to help distribute loads, right? If we're using the circuit analogy, what electrical system does a spring behave like? Well, what is a spring intended to do, right? It's intended to store and release energy, right? Now, if you had to guess, what electrical element would this act like? Now, here's my hint. Here's my hint.
Inductor?
It looks like a spring.
Inductor.
Inductor, right. All right. It's an inductor. So we're going to treat it like an inductor. So if we see springs in parallel or in series, we're going to combine them like series or parallel inductors, right? So how do we do that? Well, like this, right? So imagine for a second that a force is applied in such a manner that two springs have the same displacement but absorb different amounts of force, right? So I'm going to put a set amount of weight on this spring construction. Matt, good question. We are actually going to watch a video in a couple of minutes that explains everything, but it has to do with what we are defining as our through and across variables, right? But we'll talk about that in a minute. So, all right, if we imagine that a force is applied in such a manner to displace both of these springs equally, but each one distributes a different amount of force, right? The springs are what? What would you call this configuration? You got a 50-50. It's series or parallel?
Configuration A or B?
A.
That is in parallel.
Right. So these springs are in parallel, right? And if I wanted to make an equivalent stiffness here, right? If I wanted to make an equivalent stiffness, how would I do that? Well, I would just add them, right? I would just add the stiffnesses, right? The equivalent stiffness for springs in parallel is to sum the spring constant for all of the spring elements that are in parallel, right? Okay. So that makes sense as to why that piece of workout gear is a bunch of parallel springs, right? Because you should be able to increase the net stiffness the more springs you have in parallel, right? And so that would make it harder and that would give us more resistance. All right, so what about these springs? What are these springs? Are they parallel or in series?
I would guess series if we did parallel earlier.
Excellent guess, Dr. Zeus. Consider a force applied such that both springs have a different displacement when subjected to a different force, right? So you can squeeze these together, and if they have different spring constants, they will both have different displacements, but there's only one force being applied and going through there being transmitted. And the way that we add these together is through the reciprocal rule, right? So 1 over the equivalent stiffness is equal to the sum from I equals 1 to n of 1 over each of the stiffnesses, right? So when springs are in series, we add the reciprocal of the spring constants, right? It's important to note that when you do this, right, you'll end up with an expression for 1 over KEQ is equal to 1 over K1 plus 1 over K2 plus all the way out to 1 over Kn, right? If we wanted KEQ, we would have to do right. So just be aware, right? Don't fall into the trap of just assuming that you plug the numbers in and you get K and Q. The number that you get out of this original portion here, right? This is 1 over K and Q. You need to take the reciprocal to actually get K and Q, or KE as it is in our diagram. All right, so that's great and all, right? And in real life, right, if you were modeling a real life system, you might have to take a look and see, right? I mean, it's not that big of a deal to draw the free body diagram with all of the forces and the springs, right? But it's a lot easier if we just have to deal with one equivalent stiffness. Okay. All right, so let's watch this.
Okay, I'd like to tell you about springs in series and parallel. Let's start out with series. Series just means that they're one right after the other. And we want to be able to develop what the effective spring constant will be of the combination of these two springs. So we can treat these as though they're one spring with a particular K called the effective spring constant. Okay, so what we're going to do is we're going to put a force here of F. And when you put a force here, that force is throughout each spring. So the force is the same here as here as here. It's all the way up and down the spring. That's tension, right? So the tension is the same throughout. Okay, so what will happen then is this will stretch and that will stretch, but the total stretch we'll call X total. And the total stretch will be X1 plus X2. Okay, now if we use Hooke's law, F equals Kx, we'll ignore the negative for a little bit here. Then X is equal to F over K. And so what I'm going to say is that the X1, how much will it stretch? F over K1. And how much will X2 stretch? F over K2. And so if we wanted to replace that with one spring that had the same spring constant as this combo, that would be F and that would be K effective. Okay, well, the F's can cancel out. And so we're left with is 1 over K effective. is equal to 1 over K1 plus 1 over K2. If there were more, you'd just have plus 1 over K3 and so on. So they add like resistors that are in parallel. So they're kind of the opposite of resistors. When resistors were in series, they added, but when they were in parallel, they had the 1 over R equals 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Sometimes this is called K equivalent too. All right, let's take a look at springs in parallel. Okay, now these springs are in parallel. See how they're parallel to one another? And I'm going to put a force on here. Okay, well, when I put that force F on there, this is going to divvy up that force. And so like this will pull back and this will pull back with F1 and F2, let's say. So the forces, the force that I will have to pull, if I'm pulling these springs, I'm going to have to match this force and this force. Think of this as one person and another person. If they're both pulling with 4 newtons, then I'm going to have to pull with 8. And so if this person's pulling with 4 and that person's pulling with 4, I'd have to pull with 8. So F total is equal to F1 plus F2. And if there were more, you'd say plus 3 plus 4. I'll just do 2 for right now. Okay, well, but that's equal to Kx. So K effective times X is equal to K1 times X1 plus K2 times X2 plus, and we'll put more on if we need to. Okay, well, if this bar stays straight, then we're going to assume that when you pull, you stretch this the same as this. We're just going to assume that. And so you have to get this equation. And so when you do that, the x's are all the same, so they can cancel out. So K effective is equal to K1 plus K2 plus, and so on. This is for series. This is springs in series.
No, it's in parallel.
So they just add up. They're kind of like resistors in excuse me. I misspoke. This is for springs in parallel, and it's the same as resistors in series. Okay. All right. So
That's the proof, right? That's where that comes from. Okay, so let me ask you guys this: which equivalent stiffness, KQ, is larger given that each system uses the same number of springs with the same stiffnesses for each spring? Which one would you expect to have a larger stiffness, parallel or series springs?
Series. No, parallel. Parallel would have a higher stiffness. Oh, I'm so sorry. I didn't notice. I'm so sorry. I wasn't looking. I'll hop on the pool.
Or are you trying to mess people up? I don't know.
I'm just trying to swear everyone.
Okay.
Sorry, I was on Loud Cloud.
Right? So based on what we just learned, right? Parallel, you just add them all together. Series is 1 over, right? So parallel is going to have a larger net stiffness, right? So just be aware, right? If you're trying to think of ways that you can multiply or decrease force, right? Putting springs in series or parallel is one way of accomplishing. Looks like we're getting. All right. So what about equivalent damping? Right. Equivalent damping, very similar, right? Now, using our electrical systems analogy, a damper would behave like what? A damper, remember, is meant to resist motion, right? So a damper behaves like a
Resistor.
right? A resistor. Dampers in series get added like resistors in series, so you just add them, right? So the more dampers that you have in line with one another, the stronger the resistive force that you're going to have, right? In parallel, we use 1 over, right? We use our reciprocal rule. They're like resistors in parallel. Okay. They're like resistors in parallel. Okay. So motion inputs, right, with damping effects. When a motion input is given, it's important for us to realize that in order to create such a motion, a force needed to generate it, right? Such a motion is generated by a force that has to be great enough to generate the specified motion, right? So if you're not given, we're given some displacement input, right? We can often assume that there is some force behind it. That is to say, if you don't see an applied force, don't include it, right? If you're not told that there's specifically an applied force, don't include it on your free body diagram, but just understand that something had to cause the motion. Motion just doesn't happen, right? It doesn't just happen. All right. You guys have any questions on equivalent damping, equivalent resistance, or anything so far? You doing okay? Everybody's tracking? Right. Maybe.
Could you stay on this slide for just a second so I can get these equations
Yep.
real quick?
Yep. So let me ask you guys this question. If you were going to jump out of a window, would you rather have the mattresses stacked or the mattresses laid flat over a large area?
Depends on how good my aim was.
How high is the window?
Yes, in the limit they would want to be stacked.
So if you stack them right, you're going to get a better stiffness, but a worse damping, right? This was actually
Yeah, but you're only going to hit one mattress.
right. But so this was actually the way that my professor undergrad posed the whole stiffness in series or parallel. That was pretty. Right. So anyway, just think about that, right? I would probably rather have them all stacked personally, as opposed to being laid out flat. I'm not worried about the dampening. Or the damping, I just want to make sure there's enough cushion there. Right? All right, anyway, that should have been enough time. Right, so let's talk a little bit about nonlinearities today. Okay, talk a little bit about that. So, many mechanical systems involve nonlinear effects, right? We've talked about this a little bit. We've got Coulomb friction, gear backlash, nonlinear stiffness, the presence of discontinuous forces, right? Contact or damper forces that occur only when a mass remains in contact with the mechanical element that has stiffness or damping properties, right? Now, in this class, we're talking a lot about using ideal elements, right? Things that are just an inertia, or just a stiffness, or just a damping, right? But in the real world, that doesn't really happen. Nothing is ever really just one thing, right? Every material has its own stiffness properties, right? Like you can technically model any material with a stiffness. So how do we deal with these nonlinearities? Well, in this class, typically, we're going to what? Well, I told you that we would ignore them, right? And for the most part right now, we are going to, right? But let's run through a problem and not ignore the dry friction, right? So this is the same model that we discussed last week, right? But we're going to include friction on the armature. dry friction, not viscous friction, not damping. All right, so let's derive the equations of motion for this system. Now, if you're thinking to yourself, well, Dr. D, this should be exactly the same as the model that we made last week on Thursday, except that it's going to have dry friction as a force, then you guys are spot on. That's exactly what it's going to be, right? So we're going to have our free body diagram, right, with our mass here, and we'll have some F sub K, some F sub B, and a force that I'm going to call F dry, or dry friction, right? And of course, we have our electromagnetic force coming in, right? And we got X going this way, positive, and that's going to be equal to my kinetic diagram, right? Which my kinetic diagram will just have mx, mx. Right, so exactly the same, right? Exactly the same as our previous model from Thursday, just with the addition of an additional force, right? How many times can you say addition in something? The addition of additional force is addition, right? Okay. So does this change our inputs and our outputs at all? No, right? We still have some electromagnetic force going in, and that's going to cause a motion, right, for our solenoid valve. So we still have inputs and outputs as electromagnetic force and position. Okay. So we can write our mathematical truths now, right? And again, we'll have the classic Newton's second law. We have some damping. We have some stiffness, but we also are going to have F sub dry, right? And how do we define F dry? Well, F dry, right, is defined by the magnitude of the vector times the signum function of x dot. What does a signum function do? Well, it's a discontinuous function that returns either positive or negative, depending on the sign of the velocity, right? So that is to say that the dry friction will always act in the opposite direction of my velocity, right? Okay. Why is this nonlinear? Well, it's because the signum function is discontinuous at 0, right? If it is in fact 0, what does it return? Does it return -1 or 1 or 0, right? What's going on? And if you were to plot the signum function, right, you would get something that looks like this, right? Oh, hey. Right, so you get something that looks like that. So not continuous, right? Discontinuous at 0. All right, so how do we deal with that? Well, for right now, how does this change the way that we do our equations, right? Well, it doesn't. It doesn't, right? So we can still reduce our equations, right? So what are we going to do? Well, we'd have FEM minus F sub B minus F sub K minus F dry, right? Because we have that drawn in the negative direction, and that's going to equal MX double dots. Okay. So if we plug some things in, right, and switch around where they are. All right, lights. That's great. Cool. Apparently, one of two things is happening right now. I am either evaporating into the ether, and so the lights don't recognize that I'm in the room anymore, or the lights have broken. It's probably, so if I disappear, just let them know that something happened and I just evaporated. One sec. Perfect. That's fine. We're good. We're good. So we can still plug things in like that, right? We can still do that. It's not a big deal. right? We just can't analyze this, right? So we have the model, we just can't analyze it right now. So what we're gonna do, right, and typically what we're doing for right now is we're just gonna ignore dry friction, right? We're gonna ignore the nonlinearities. And that'll be okay, we're gonna actually, when we start plugging things in through evaluations, right, in MATLAB and whatnot, we're gonna run some systems both linearly and non-linearly and see what happens, see how far off we are, see if it mattered. Right? But for right now, if you're given something with dry friction, this is fine, just leave it, that's it, that's the model, right, move on. Non-linearities don't affect us until we go to evaluate things, right, is the point. Right, we don't want any nonlinearities when we go to evaluate our solutions, because things like state space equations require us to have a linear system. Right? They require us to have a linear system. Things like Laplace transforms also. Okay. You guys have any questions on this?
So in the sense of like these non-linearities, you're just saying that like the input and output and the overall stuff doesn't, like the stuff we're looking for doesn't change, it just changes like the values because it comes and introduces new stuff into the system.
Yeah, so right now, right, this portion doesn't have to be linear, right? So if you're making this model right now, this is a nonlinear model because of that signum function, right, Carl? But it, we don't need to linearize it unless we're going to take it further than this, right? So for right now, it's okay to leave it like this. Once we get into like week 6-ish, when we start doing time domain analyses and we want to work specifically with linearly time invariant systems, then we're going to have to start linearizing these things over small intervals, right? Using small angle approximations and whatnot. Small changes from our equilibrium. You guys have any other questions? Because we're gonna jump into a bunch of problems. This is a jump. Say head first a bunch. No? Everybody doing okay? Okay.
Yes.
So let's take a look at this wind turbine. Right, so here's a wind turbine generator used for transforming mechanical energy into electrical. We're going to assume that J1, right, and J1 is the turbine blades, and J2 are rigidly connected to their respective gears. Okay, so the gear train itself, this is telling us what? That this is an ideal gear train, right? Because we're going to lump all of the inertia from the turbine and that first gear into a single inertia. And we're going to lump everything from the generator and that attached gear into a single inertia as well, right? Why? Because it eliminates having to deal with backlash. Right? We don't want to deal with nonlinear backlash. So derive a mathematical model. Right? So let's do that together. Right? So I've got this turbine. Right? I'm going to need 2 free body diagrams here. Right? I need 2 free body diagrams. So let's start here. This is going to be J1. It has some radius that we're going to call R1, right? We're going to assume that everything is, we're going to analyze this all at the gear interface, because that's where we're transmitting our power, right, at that gear interface. So that whole left-hand side, that whole turbine, right? So here's my turbine, right? write turbine correctly. So that's the FED for the turbine. Okay, and I'm going to say that this is going to be moving in that direction. I'm going to consider that as such, right? So let's go back and let's look at our schematic one more time. So look, I've got some arrow, some T arrow, right? Some torque produced from the wind, right? And that looks like it's spinning in the direction of motion. And there's some bearing friction here as well, B1. So I should probably account for those. So let's do that, right? My input here on this is going to be the wind, right, which is T arrow. And then I've got some damping, which is going to oppose my motion. And I want you to notice that this here, right, this theta 1, that's serving as my coordinate system. That is letting me know which way I'm considering to be positive for this. Okay. Could you do it with a standard Cartesian? Sure. It doesn't matter. Just follow your signs through. Now there's one force that I'm missing here, right? There's one force that I'm missing here. So what force do you guys think that I'm missing?
Friction?
Not friction. No, we're gonna assume that friction is negligible. Dry friction is negligible. The friction's taken into account through our damping, right? Our bearing there. If you were removing this, right? If we're making a free body diagram, I had to remove this from my system, right? What is a support or reaction force that I'm missing from this? Remember, this is the turbine, right? There's also the other half.
Oh, you're missing the entire reactions system that's mounting that.
Right. So I'm going to have this force here. And I'm going to call F sub C, which is my contact force. Those gears are touching, right? Those gears are touching. The gears have to touch, and therefore exerting an equal and yet opposite force on one another, right? And so this is R2 in there. If we were to go back, we would see that there's some generator torque here. We also have some damping, PB2. We have an equal and yet opposite force here. And I'm actually going to say that this, for this half, I'm going to change my coordinates and do it that way. Is that legal? Sure. Choice of coordinate system is arbitrary based off of FED. All right. So let's talk about how this works for a second again, right? Because I think that'll, right? So is T gen an actual applied torque, right? Is that an applied torque? No, that's the produced torque, right? I get some torque from the wind, right? And that's going to be converted into some torque that gets fed to the generator, right? And we're talking about the generator rotor. Cool. All right, so everybody okay with this, right? If I wanted to draw a kinetic diagram, right, this one would have J1 theta double dot 1, and this one would have J2 theta double dot 2. These are solely rotating, right? This is not translating. At least I hope your wind turbine's not translating. That would be pretty poor design, right? I don't know. I'll talk to Professor Tomford. I know nobody in my dynamics class had any translating thoughts, but you know, maybe in her class there might have been one or two. Let's see.
What is the damping in this scenario?
The bearing friction. Right, so we go back to our schematic here. It's called out here. So we've got bearing friction here, and for the generator, we've got some thin film between the housing and the generator rotor.
Got it.
Okay. Now that contact force is very important as it serves as a way to couple the two systems, right? That's the force that we're transmitting. Doesn't matter if I draw it one way or the other, right? Doesn't matter if I have, no, they're internal forces, right? As long as they're equal and opposite, it doesn't matter because they are going to essentially cancel when we put everything back together, right? So the only constraint for those internal forces is that they have to be equal and opposite. You can choose them in whatever direction you want, just make sure it's consistent with how you have created the system, right? All right, so let's talk about inputs and outputs, right? Inputs and outputs. What's my input? What's my input?
Torque. Wind.
Right, what is the wind? Well, what's the wind producing?
Torque.
It's the T arrow, right? Remember, it's only the stuff that we have on our free body diagram, right? So if you're looking at your free body diagram, you better have your input and your output labeled on here somewhere, because if it's not on this free body diagram, I should not see it in your equations, right? That's what we're wanting to do, is we want to make free body diagrams that are clean, right? They only have the information on it that we need and that we want. All right, so my output. Well, in this case, we've got two, right? We've got T generator, right? That's our torque output, but we also have this idea of a local output, right? So if you broke this into parts like J1, the output from J1 is not T generated, right? It's the contact force. We're putting in some torque due to the wind, and we're getting that contact force out. That contact force is then driving the generator and producing T gen, right? So we actually have this idea, right? These are global, right? These are global inputs and outputs, whereas these are local, right? Global meaning overall, in the grand scheme of things, I'm putting in T arrow and I'm getting out T generated, right? But if I'm breaking this down into pieces, right, I'm going to have some output of FC on J1 and some input of FC on J2. Okay.
Is this true for any time you have like a meshed gear set for the localized forces right there, in and out?
I'm sorry, you say that one more time?
Is that true for all meshed gear? Like anytime you have two gears that are meshed together, are you always going to have them in the input and output? Or is this?
Anytime that you have gears, you're going to have some contact force, right? And so you'll have something driving it, and each gear is going to have, right? So we can talk about it in terms of F sub C. What we're going to find out, right, really is that this is going to break down and let us start talking about gear ratio again, right? Because the ratio of the gear ratio is what, like we talked about the other day, the gear ratio allows us to transform an input torque into our output torque, right? So we'll see that gear ratio is actually going to pop up here in a minute once we start working through the reduction. So what are my mathematical truths? Right? Well, some of the torques, J theta double dot, the torque of B in general, right? I understand that we have two of these, right? So TB1 is going to be B1 theta dot 1 and TB2 is going to be B2 theta dot 2, right? They're not interplaying with one another. Do we have any stiffness in here? Do we have any stiffness here?
Yes, if you're including the dynamics of the actual wind turbine, you know, as a spring system.
All right, so true, we could, but is there any stiffness called out on the schematic?
No.
And this is where I say, Danny, at what point did you think that these problems were happening in the real world? All right, these are ideal right now. Okay.
Well, I mean, technically, well, I don't know. So in my mind, you said you're going to take the whole turbine to gear as one system, but there would definitely be some sort of spring torque in the shaft.
Some sort of stiffness for the shaft, 100%. But it's not called out anywhere, right? And general rule of thumb is if you don't see it called out on like a schematic like this, I would just not include it. Reason being is we're going to take these schematics, we're going to go on later in class to create our models, right? And then we're going to run them through. And if you're not given a value for the stiffness, don't make one up just to get a result, right? You probably just shouldn't include the stiffness, right? And there's a reason why we're not including the stiffness, right? When we lump everything together, we lose that shaft, right? When we create one lumped system. Right. So we don't need a stiffness truth. These are our two truths. And what we're going to find out is something pretty nice when we get down to the end. So what do you guys want to start with? You want to start with the generator or the turbine? I'll let you guys pick. We start with the generator or we start with the turbine here?
Generator.
With the generator, all right. Interesting. Didn't peg you guys for generator folk, but that's cool. All right, so for our generator, what do we have? We have to sum our torques, right? Sum of the torques is equal to J2 theta double dot 2. All right, so let's go back to the free body diagram for the generator. Let's look at it. What are my torques? What torques do I have working on this, right? Well, there's the two obvious ones, right? There's T-gen and TB2, all right? Easy peas. Is that all of the torques? Is that all the torques? Trenton, what do you mean by the gear torque?
Oh, I was talking about that for the question you had a long time ago about what force are we missing, the contact, the gear contacts.
Right. Okay.
But for the question I think you have now is it the gear contacts that are another torque that we have to account for?
Yep. That force is a perpendicular distance away from the axis of rotation, right? So that force is going to create a torque, right? It's going to be FC times R2. Is it going to be positive or negative? Well, in this case, we have
Positive.
this direction listed as positive, right? So we're going to leave that as positive torque. So if we go to write our generator equation, we'll have FC times R2, okay, minus TB2 minus T-gen is equal to J2 theta double dot 2. All right, remember, I need everything in terms of what? Well, I want everything in terms of my inputs on one side, my outputs on the other, right? So I'd want J2 theta double dot 2. I can substitute in for this plus B2 theta dot 2 is equal to T gen plus FC, right? And now I'm going to do something, well, we'll do that in a minute. So let's call this equation 1, right? That's fine. So that's, I guess we'll do the turbine. We'll just do the turbine right underneath. I'll do it in a different color so it doesn't look exactly the same. Here's my turbine equation, right? So we'll go back, we look at our free body diagram, and we're going to grab the sums of the torques, right? What I've got, well, same torque. So I've got T arrow, which is positive. I've got TB, which is negative. And I've got FC times R1, also negative. So let's write it out. T arrow minus TB1 minus FCR1 equal to J1 theta double dot 1. Right? So we're going to keep this in terms of our, I'm sorry, this should be plus, not minus. I looked at the wrong. Nope. Sorry. Can't read my own notes, guys. I can't read my own notes.
Dr. D,
Yeah.
why is it that the sign convention on the generator torque changed? Or is it still negative for the generator?
No, that should be negative. I just didn't write it. My bad. Sorry. I'm just so excited. It's going so fast. I'm so excited. It happens. All right. So we're going to algebra this, right? So J1 theta double dot 1 plus B1 theta dot 1 is equal to T arrow minus FC. Equation 2. All right, and normally I would tell you, hey, that's cool. We can just leave that, right? That's fine. But we're not going to do that today because I'm going to use this time we're going to make a point with this one, right? Because we can make, this one's not that bad for us to get one complete master equation, as it were. Right, because I mean, it's great that we can talk about contact force, right? But I don't know what that contact force is, right? And measuring that contact force seems kind of like a pain in the butt. So I'm going to put these things back together and get what I'm really after, right? I want to know how much torque do I get out based on how much I put in, right? So to do that, what do we have to do? Well, we need another equation, and that's going to come from solving one of them. We're going to solve one of these equations for F sub C, and then we're going to plug it in to the other one, right? So what I'm going to do is I'm going to solve my generator equation. I'm going to solve equation 1 here for, I'm going to solve that equation for F sub C. Okay. So solve equation 1 for F sub C. Do that. I'll get F sub C is equal to J2 over R2 theta double dot 2 plus B2 over R2 theta dot 2 plus 1 over R2 T generator. I'll call that 3. Call that 3. Cody Wood. How do I do what without knowing the ratios? Does it matter what they are for me to just do the math? Can I just plug them in later to figure out what the ratios are, like, and figure out which one's moving? Right. Essentially, you'll know the radius of each of those gears, right? If you're designing the system, you should know what you should have some target that you're going after, right? This is to show you can use equations like this, right, when they're done symbolically to plug in different values to see how they affect your outputs, right? When this is going to be more important is less in the modeling stage here. That's fairly trivial here. We can determine, well, if R1 is bigger than R2, then we'll have, you know, something that's moving faster or slower, right? But once we get into the time domain responsive stuff, that's when we can't rely on gut feeling anymore. And these things are all, these parameters are all going to change the basic root response of our system, which determines the stability of things. And we'll get into more of this later, right? But I guess to answer your question, none of these numbers matter right now. They can be whatever I want them to be, right? The important part is you setting up the equation symbolically, because if you can set it up symbolically, then it's just plugging in a number later. Right? That's all that it is. Okay. So then we're going to plug 3 back into equation 2, right? Because it wouldn't make sense to plug it back into equation 1 because, right, that's going to give us back what we started with. So we're going to plug 3 into 2. And if I do that, I'll get this nasty looking beastie right here. And look, okay, it's starting to come together. Right, we're starting to see some gear ratios out here. All right. Now I have everything in terms of my outputs on one side and my inputs on the other, right? Kind of. But we're not done, right? Because we can do some other stuff here. Right, because yeah, having things in terms of theta 1 and theta 2 is messy, right? I want to pick one. I want to pick one and just figure it out. So I'm going to say that from rotation about a fixed axis in our dynamics class, right? So when things are spinning about a fixed axis, right, this is a specific class of motion called rotation about a fixed axis. It's not translating, it's just spinning. And because of that, what do we know, right? Well, we know that the velocity, the angular velocity, theta dot 2, in this case specifically. So I'm going to write this down from Rafa, rotation about a fixed axis. I know that theta dot 2 is equal to R1, R2, plus theta dot 1. This is something that we derived in class last week on Thursday, I believe, when we talked about transformers, right? We talked about ideal gear sets. The output angular velocity is the gear ratio, right, times the input velocity, right? So I can plug in for theta dot 2, right? I can plug in this R1 over R2 theta dot 1. And for theta double dot 2, I can plug in R1 over R2 theta double dot 1. Right? Because the acceleration is just going to scale by the gear ratio as well. All right. So we can keep this going, right? So why would I want to choose theta 1 instead of theta 2? Well, because that's the input, right? That's the input end. I want to say, well, I've got some known torque due to wind speed. I can readily measure the angle that I have traveled through of my wind turbine, right? In fact, most wind turbines are set up to have at least an accelerometer. so that you can get the angular acceleration of said turbine, right? It's a lot harder to instrument the inside of the generator to get what theta dot and theta double dot would be for the generator, right? Okay. So we're gonna plug stuff in again, right? We're gonna plug stuff in. J1 theta double dot 1 plus B1 theta dot 1 plus R1 over R2 times R1 over R2 J2 theta double dot 1 plus R1 over R2 R1 over R2 B2 theta dot 1. This whole thing is equal to T arrow minus R1 over R2 T generated. Okay. Right, we talked about it earlier, but N is equal to R1 over R2, right? That's my gear ratio. So I'm going to plug in N anywhere that I have R1 over R2. Right? So if I do that, well, let's take a look here, right? I can group these two terms together, right? Those are both being multiplied by theta double dot 1. I can group these terms together, right? Because those are just theta dot 1 terms. Okay. So why don't we do that? We got J1 plus N squared times J2, right? Because R1 and R over R2 is just N, and N times N would be N squared. That whole thing is theta double dot 1. If I do the same thing for my theta dot, right? Well, I've got B1 plus N squared B2 theta dot 1 is equal to T arrow minus N T gen. Okay. Now that's all well and good, and why, right? Why do that? Well, turns out that I can take this term here, and I can call this J EQ, and I can take this term here, and I can B EQ. Sometimes you'll see it as BCL for composite, right? They're equivalent or composite inertias, right? So the entire system, right, the whole inertia of the entire system can be rewritten as JEQ here, which is J1 plus the gear ratio squared times J2, and B1 plus the gear ratio squared B2 for BEQ. Okay. So this is the idea that we can take this larger system and we can actually lump it down to a single inertia in a single damping, right? Now the other thing that's neat about this, which what I think is nice, is we can do a change of dynamic variable on this, right? So knowing the position, that's great and all, right? But really, when we're talking about wind turbines, aren't we really more concerned about the angular velocity? Well, how would I do that, right? Well, this is equivalent, right? This is equivalent to me saying J EQ omega dot 1 plus B EQ times omega plus N T gen, right? Because I want inputs on one side is equal, I'm sorry. I want outputs on one side is equal to
Sorry, I think I missed it, but where did the secondary R1 over R2 come for the expanded formula?
Sure. So this right here. or
Yeah.
that- well, there we go. Don't do the thing on me. Okay, thank goodness. Came from here. So I'm going to take this theta dot 2, right? And I say that, well, because it's rotating about a fixed axis, I can use the gear ratio to multiply. So I can multiply my input angular velocity by my gear ratio to get my output, right? And I can plug this in here. And now everything will be in terms of theta dot 1. If I take the derivative of that, I can plug it in here. Right, and so now you'll end up with R1 over R2 times R1 over R2 theta double dot 1 times J2 there. And you'll end up with R1 over R2 times R1 over R2 B2 theta dot 1. Right, so I'm changing the theta dot 2's and the theta double dot 2 into theta dot 1 and theta double dot 1. Right, and the reason for that is I want everything to be in terms of that first angular position, right? The reason that I gave is because it's easier to measure, right, in real life. Right? So it's a lot easier to measure how fast your turbine is moving, right? And the change of dynamic variable here is just that easy, right? I know that theta dot 1 is angular velocity, so I can just plug that in. What happened if you, how would you do that if you had a stiffness term? Well, you can't really. You can, but you have to have the integral of position as one part of your equation, which would be gross, and we don't really want to do that. Any other questions? No. No, everybody doing all right? Maybe. Everybody's super lost and doesn't want to talk to me. Probably. Yeah. At least you guys are honest.
It's been a long morning, that's all.
That's good. Okay. Alrighty. So, that being said, we're going to move on then to the next problem. Right. Let me get my sheet over here. Next problem. Now, like I said at the beginning of class, I don't want you guys to be frightened by the week 2 example problems. Really what I would like is for somebody to start by trying the free body diagram, and we will discuss how to do it once you hit a stopping point, right? Once you get a sticking point, that's fine. I'm not expecting you guys to be able to work through everything perfectly, right? But I wanted to give you guys these problems so you could try them ahead of time. Right? So we want to create a mathematical model for this. And Rowan, you were the one who was randomly assigned to this problem. Would you care to try to start out the free body diagram? You can hit the annotate button on the screen on the top and try to draw it as best as you can with the mouse. I know it's not great, but it's what we have. Cody,
I'm gonna go get my mouse real fast.
Cody, I find your use of chat strange. Please try to keep it, adult and, related to questions of the class. Also, just so you guys know, I do get a report of chat after class, and I can see like private chats. So just in case you guys were wondering about that. Okay, cool. So Rowan, I'm sorry I didn't hear you. What was that?
I just needed to go get my mouse.
I know it's not. If you did it on paper, you can hold up your paper too. That's
Oh,
fine.
yeah, I have it on paper.
Cool. Cool. Let me stop sharing so we can take it. And so, yep, there we go. All right. Trenton, this problem should look a lot like lab 1, right? So Rowan, your free body diagram is looking pretty good. It was a little bit fuzzy, but I think I got most of it. So you've got a mass hanging down, right? You've got a spring force on each of your pendulums that are equal and oppositely directed, right? Now, can you throw it up there one more time so I can take another look? Kind of. So what do we got going? Can you like explain it a little bit to everybody? See what's on there?
Yeah, so I had like a force maybe going the opposite way of the way they were moving because of gravity. I wasn't exactly sure. I thought maybe that there would be a force going the other way. So that way.
Sure. So we don't need that extra force. It's going to be the component of gravity, right?
Okay.
There is one force that I think you might be missing. It's one or two forces depending on how you drew it. Either the reactions at the pin or the tension in the cable, right?
Oh yeah, I have the tension right there.
Yeah, sorry, it's just, oh yeah, there it is. All right, cool, cool. All right, yeah, I mean, free body diagram looks good. Good job. So as far as inputs and output goes, what would you think are the inputs and outputs?
I thought the outputs would be the theta 1 and theta 2.
Yep.
And I wasn't exactly sure what the input would be.
So that's a tricky one, right? The input is actually going to be the weight, right? Because that's what's driving, remember, that's what's driving the, wait for it, I'll get there. So it's driving the motion. It's driving the motion. All right, and Cody, I apologize to you for earlier, but there's no preload in here, right? Because there's no spring. So no preload. All right, cool. So we've got our free body diagram. I'm gonna quick draw it up here, just so we can we'll all see it, right? Wait for it. Oh, man. My notes are all sticking together, right? So we've got for mass 1, I'm gonna call this point up here, well, we'll talk about that in a second. So here's this guy, right? I've got some force F sub K, right? I've got some mass, mg. I know that this is moving through some angle. We'll call that theta 1, right? There's some point up here. I'm going to call it C. You can call it whatever you want, but I need it because this distance is given to us, right? As L1. And the entire length from here to here is L2, right? So that's mass 1, all right? We'll annotate this again in a second. I'm going to call this mass 1. And then some distance over here, I've got this point D, right? It's a different point. Oh, I forgot. You need that tension. The tension's got to be in there. We'll call it T1. And at some point over here, I've got a very similar looking scenario, right? Where I've got F sub K, I've got some mass 2 times gravity. I've got, again, that same distance L1 and the entire thing from top to bottom. and some other thing, right? So I've got something that looks like that. Now, what coordinate system do you guys fancy for this, right? Ron, what did you use when you drew yours? Just normal Cartesian?
Yeah.
And that's not a bad choice, but it's not the best choice, right? You can certainly do this with a Cartesian coordinate system, but if you use a normal tangential coordinate system, right? If you use a normal tangential coordinate system, this gets really nice, right? Because for each of these, I am going to take the moment about, or the torque about the rotating point, right? The axis of rotation. That makes so many forces disappear, right? So if you had me for statics and dynamics, you know my Dr. D's #1 rule about where to take your moments, right, is to make sure you're taking it at the point where most of the forces pass through, right? That way we don't have to deal with it. So that applies here, right? But in general, this is what we're looking at. So I'm just gonna kind of say, well, this would break down, right, into components like that, right? Normal and tangential components, right? So I'm gonna have those. And my spring force is actually gonna have some normal and tangential components on it as well, right? So again, you can do this in Cartesian, right? And that would work, but you're gonna have to carry a lot more sines and cosines. Whereas you'll see in this case, there's only one sine and cosine that we'll have, and we're actually going to linearize it out of there. Good stuff. So I don't know, say we had like a pendulum without a spring, like a single pendulum without a spring, right? I don't know when you would ever see that, but if you did, right? It would look pretty similar to this free body diagram, right? You would just remove the spring. You just remove this. Right. So we got our inputs and our outputs, right? We talked about this. I'm leaving that free body diagram up there for a second on purpose. Hopefully it's still up there. Your input is technically that mass times gravity, right? Your output is, or some people might say it's theta 1, right? I'm going to move it a certain distance, and that's my input, and my output's definitely theta 2. Right?
Question. So tangential, I guess, coordinate system, you're just taking out the angles that you would have seen otherwise, or I guess what's the point?
So for a normal tangent, so all right. So when is it appropriate to use a normal and tangential coordinate system, right? That's the question. You want to use a normal and tangential coordinate system for circular motion or curvilinear motion that is constrained along a path, right? In this case, imagine that this pendulum was allowed to swing freely in 360 degrees, right? It would always, the path would always be constrained to the length L2, right? Because assuming that that's a rigid length, right? So this path never changes, right, as it goes around. You would want to use something like radial transverse coordinates when this path can be oblong, right? So this can slide in and out, away and towards, right? What does normal and tangential do, right? Well, at any point along its path, right, say it was here, say I had my pendulum here, there's always a component that points tangential to the path of motion, and always one that points back towards the axis of rotation, right? So anywhere that I go around here, my coordinate system relative to the ball remains unchanged, as opposed to using Cartesian coordinates. Well, now in this, I've got different components here, right? And my angle is constantly changing. Now I need to know at every point in time, what is that angle right? I have to make sure that I'm tracking my sines and my cosines correctly for every time point that I'm interested in, right? It's a way of simplifying it. Is it wrong or right? No, it is, right? It's not, you're not incorrect if you use Cartesian, you're just making more work for yourself, right? Just making more work. You can totally do it with Cartesian if you wanted to do it, right? And that's fine. And like I said the other day, whatever coordinate system you put on your paper is the one that I will hold you to check your work, right? So whatever coordinate system you use, I will check it using that coordinate system. But just for your own clarification, there are certain coordinate systems that make things easier. So I'm going to use this theta 1, right? Theta 1 as my input and theta 2 as my output. Could you make an argument the other way? Sure, it's fine. That's fine. Right. So we get to our mathematical truths now, right? So, okay, Rowan, what did you choose as your mathematical truths, or did you not? Did you get to the inputs and outputs and just call it for the day?
I did not get to the truths.
That's totally fine. Thank you very much for at least doing, for getting the free body diagram. I really am glad that you guys, so far, with the sample size of 1, are 100% on at least trying. All right, so what do? Well, this is a rotational problem, right? We're going to rotate about some point, and so we'll have torque. Some of the torques is J theta dot, right? Now here's where it gets a little bit tricky, right? Because that spring, that's a translational spring. That is not a rotational spring. And so the distance, right, that force Fk is equal to K times, and the way that I've drawn it, I've assumed, all right, so let's go back to our thing here. All right, so if I've drawn it this way, it's pulling in, right? So that means it's in tension. The way that this is going to be in tension is what? Well, that means that theta 2 has to be larger than theta 1, right? So I've assumed that theta 2 is greater than theta 1. Does that make sense, right? The second pendulum is moving further than the, now, based on the way that it's drawn, right, you would say, well, Dr. D, that's not the way that it's drawn, right? It's clear, very clear to me that theta 1 is larger than theta 2 at the moment that this is drawn. And that's fine. You could pick the other way too, right? But if you draw your spring pointed the way that I have, you have assumed that theta 2 is greater than theta 1. That's what you have assumed. Okay.
I have a question. I don't know if I'm being dumb, but where is the angle 2 on the second? Or are we just not supposed to have it on the free body diagram?
There it is. It's supposed to be there.
Okay.
And it uses, so when I draw the coordinate system in the middle-ish like this, I'm saying that this is for both of these diagrams, right? That's what I'm going with. Good catch. All right. So I've assumed that theta 2 is greater than theta 1, right? I've assumed that theta 2 is greater than, right? But that's a force, right? That's a force, right? So that's going to be defined by this equation, right? X2 is greater, X2 minus X1, right? I've translated more on the second half than I have on the first half. All right, all right, all right. But that's got two problems. First, it's a force, right? And I need torques. And second, it's a function of X and I want it to be theta. So I need to convert the force to a torque and I need to convert X to theta. How do I convert X to theta? Well, it turns out that we can use this equation, right? And why can we use that equation? Well, we are going to assume that we're going through a small angle, right? Again, remember, we are assuming that we're starting at equilibrium and then this swings through a small angle, small changes in angles, right? Our linear approximations are good through small deviations from our equilibrium point. That looks like the equation for arc length, right? Well, yeah, it is, right? But if you zoomed in close enough, the edge of a circle would look flat, right? Case in point, the Earth. That's right, I said it. The Earth is round, people. At me in the comments, all right? That's what it is. All right, anyway. So we can use this, right? And how do we make a force into a torque? Well, if I want the torque for this spring, isn't that just going to be my force times the perpendicular distance? I'll call it L perp, that it is away from the wherever I'm taking my moment about, right? Yeah, interesting, interesting. Well, in both cases, isn't that distance just given to us as L1? Okay. So we've got some stuff to work with here, right? And the next part of this, right, is essentially we're going to pick either mass 1 or mass 2, and we're going to reduce our equations, right? And then once we're done doing that, we're going to do rinse and repeat on the other one, right? All right, is everybody okay so far up through the mathematical truths? Does everybody understand where this comes from? Another way of thinking about this X position, right? If I had a wheel that was rolling, right, it would be translating by some position X, right, as a function of its rotation, right? Well, it's tied in through so if this, how much does it translate based off of the rotation? Well, it depends on the circumference, right? So in one revolution, I will have 2 pi r distance, right? The pi's will cancel and we'll be left with x. X is equal to L times theta. Theta is equal to x over L. It's generated from the circumference of a rolling disc. Okay, so we'll start with mass 1. We're going to start with mass 1. So for that first pendulum on the left, what do we get? Well, if we're going to sum our torques, right? Well, J1 theta double dot 1 is equal to what? Let's go back and look. Let's go back and look at our free body diagram. All right, so I've got a couple things here. So because I'm using normal and tangential coordinates, and I'm going to take the moment about this point C up here, right? Remember, I can take the moment about any point that I want. It makes sense to do it from C for a couple of reasons. One, I have all of my distances known from C, right? I know them, and they're not going to change, right? C will always be L1 away from where my spring is, and will always be L2 away from the base of the pendulum. The other reason is because I've used normal and tangential coordinates, this goes away, and this tension goes away, because they do not contribute a moment at point C, since they all pass through point C. Okay, so what are we left with? Well, we're left with this force, right, which the tangential component is just m1g times the sine of theta 1. And we're left with this guy here, right, which is going to be fk times the cosine of theta 1, right, because this is the angle in there. I know that that is small and probably hard to see. And so we are looking at this, right? We are essentially, because of the coordinate system that we've chosen and the place that we've decided to take our moment about, we have reduced this from a system of, 1, 2, 3, 4, 5 forces to a system of 2 forces that are contributing moments, right? And that's what's important for us to consider for this problem. All right, so let's look at this, right? What's up?
I just have a question about, so because now to get a better understanding of this, you you did that, you canceled all of those just because our moment about, we chose the moment about C, right?
Yeah.
Okay.
Yep. Remember, anytime that you have forces passing through the point that you're going to take the moment, right? That perpendicular distance is 0.
Okay.
They do not contribute a moment, right? They do not. Okay. Cool. So. Looking at this, one last thing, looking at this. Oh no, did I do the thing? Okay, good. Sometimes if I switch slides too fast, it does the magic tablecloth trick where it leaves one slide drawings on. All right, anyway, you guys don't care. Okay. Here's my pendulum, right? It's pinned up here at the top. My weight is pushing this way. Is that a positive or a negative moment?
Positive.
Positive or negative? It's negative, right? It's going against, right? So this force is pushing this way, right? That's going to cause a rotation in this direction, which is counter to our positive here, right? Clockwise is a negative rotation. All right, so that's negative, right? What about up here, right? I'm pushing this way. Well, the spring force actually produces a positive rotation, right? The spring force, if I'm pushing here towards the center, right, it's gonna give me a positive torque. So let's go down and reduce this equation, right? So I've got to sum my torques, right? Well, I have negative M1 times G, right? That's my force times sine of theta, right? Because this is my force. The force was M1G sine theta. It's negative because I know it's a negative torque. But this whole thing, this force gets multiplied by the distance it is away from the point about which I'm taking the moment, which was L2. Likewise, I'll end up with F sub K times L1, which is my torque, times cosine of theta. Okay. And now this is where I will do a math magic, right? And I will say, well, you know how we were talking about small angles? Well, the small angle approximation, what does that tell me? Well, that tells me that the sine of theta, well, what's the sine of a small angle? Well, it's actually equal to theta. And what's the cosine of a small angle? Say it's approximately 1. What constitutes a small angle? Great question. 5 degrees or less. It's interesting how the lab uses 5 degrees, isn't it? It's very interesting. Right? So if we apply the small angle approximation here, we can linearize this equation, right? And for a small angle, that tells us what? Well, that tells us that we get negative M1G L2 times theta, okay, plus, and I'm going to substitute in my kx here, but remember, f sub k was just k times x2 minus x1, which we are going to rewrite as L1 theta 2 minus L1 theta 1 times L1, because cosine of theta at small angles is approximately 1. Right, so we'll continue some algebra, right? Continue with some algebra here. Sorry, that should be theta 1 plus k L1 squared theta is equal to k L1 squared theta 2. It's theta 1 and theta 2. So I've got theta 1 on one side, theta 2 on the other, right? If I really wanted to, right, I could do some hardcore algebra. There you go, M1G L2 plus K L1 squared theta 1 is equal K L1 squared theta. Right. And essentially, right, you could, if you wanted to, say that this was an equivalent stiffness, but we're not going to say that. We're just going to leave it as is. If you got it that far, and you put the, heck, even if you got it this far, right here, if you left it like this line right here, I would accept that for full credit.
Dr. D, in that line, that second K, that K1 squared is supposed to be L1 squared, correct?
Which one now, Josh? Sorry.
The one at the end next to theta 2.
Yeah, that's an L. Sorry, not K. That would be weird. Sorry about that.
All good. Just wanted to double check.
Oh no, yeah. Yes. That is definitely an L, not a K. Apologize. Frankly, I'm a little concerned that that you even no, I'm just kidding. Thank you for pointing that out. That would have been very confusing for a lot of people trying to study later and being like, where is this other K? And then that. Okay. All right, so cool. That's the 1/2, right? That's the 1/2 of it. So what do we do now? Well, we're going to do the same exact thing for the second pendulum, right? And you're going to have this model that is connected through theta 1 and theta 2, right? Because unsurprisingly, I hope, you would see that if I move one of the penduli, then the other one has to move as well. If I move one pendulum, the other, they're connected, right? They're connected by some spring, right? So there's some force transfer going on through there and some change in wait for it, I'll get there, in position. All right, so let's look at mass 2, right? Let's look at mass 2. Okay, so mass 2.
Dr. D,
Yeah.
can you go back to that last slide for just a quick second? I had to finish the last slide.
Nope.
Thank you.
Yep. All right, so if we're gonna go back to, you guys can all go back and look at your free body diagrams, right? And what you're gonna notice is what? Well, we still only have the two forces that are acting there, right? Now, instead of taking the moment at point C, we're gonna take the moment about which the second pendulum is rotating, what I called point D, right? Those were arbitrary. You can call them whatever you want. Does not matter. Does not matter. Right? That I am fairly certain it's not a hyperbolic paraboloid. We're not talking about catenary cables right now, so you don't have to really worry about that. Okay, so if we're taking the moment about point D, right, we're going to notice a couple of things. First of all, we're going to notice that our weight is still pointing down this way, right? And our weight is still going to cause a negative moment, right? It's going to be M2 GL2 sine theta 2, right? But our spring force is now also pointing in this direction, which means that it's also contributing a negative moment, right? That's what that means. So let's start looking at this, right? So I've got J2 theta double dot 2 is equal to negative M2G L2 sine theta 2 minus FK L1 cosine of theta 2. Okay. And now we're going to do the same things that we did before, right? We're going to plug in for F sub K, which we know already, right? And so we'll just keep running it through. I'm going to apply my small angle approximation, right? just in case we forgot, that sine of theta is approximately theta, and cosine of theta is approximately 1. So I'm left with this minus k times L1 theta 2 minus L1 theta 1 times L1. Move some things around, get all the theta 2s on one side, all the theta 1s on the other. And we can leave it like that. It's fine. It's fine. But what if we were doing this like, I don't know, for like a lab, right? And you needed to get numbers out, right? You had to plug numbers in. Wouldn't you need to come up with an expression for J, right? Don't you need to know what that moment of inertia is, right? Well, it turns out that J for a point mass is m times L squared. So it's the mass times the distance it is away from some point squared, right? So for this case, right, for this example, we would have J1 is equal to M1 L2 squared, and J2 is equal to M2 L2 squared. Presumably you would know the mass of the pendulum, right? Presumably you know the length because you measured it. So you can, that would contribute, right? And we could plug that back in and throw it back in as well. Like I said, on an exam or in a homework, if you got that equation that's right there, I am very happy with that. Unless you are specifically asked to find like the equivalent stiffness for this system, right, then don't worry about it. If you wanted to do the extra algebra, that's fine too. Depends on how you want it to look, what aesthetic you want. Now, I will say there will come a time when it will be nice to have it broken down, and you continue and do the algebra all the way until you get something that's theta double dot and just theta when we get to the Laplace transforms, but it's not overly concerning. It's just another algebra step. You guys have any questions on this? Everybody's okay, maybe. Right? Everybody's okay, maybe?
I have a question not about like this problem, but it's just like, well, we got like 20 minutes left or something. Are we gonna keep on just doing these throughout the week, or are you allowed to post another form to check our answers if ours is right? Since this is like the only.
Yeah. Carl, we're gonna keep doing these. Like the handout I gave you is mostly what we're gonna do in class. The ones that we don't get to in class this week, because we're probably not gonna get through all of them, I am gonna post at the end of the week hand done solutions for each of them, so you guys can. I would still highly recommend trying them on your own, right? And then, general study tip, right, is try a bunch of problems and don't go through it with the solution the first time. Try it yourself and see where you went wrong, and then continue going, right? Be a general tip. But yeah, I will post solutions to all of these problems, whether we do them in class or not at the end of the week. But the plan for most of the week is we're just gonna do problems. Matt, what's up?
I'm looking at the pendulum lab assignment and it wants us to actually construct a pendulum. Is that still the case?
So instead of you constructing the pendulum, that's why Professor Price and I did it and put the video on YouTube about it.
Oh, is it in the announcements or something?
Yeah, so if you go on to the YouTube playlist link that's in the announcements, you'll see Dr. D and Professor Price do labs episode 1. It's got a sweet thumbnail with fire and Funko Pop on it.
Oh, okay, cool.
So if you watch that, that is us running the lab portion. So you guys just have to take data off of that and then apply it to your model.
Okay, so you give us the data from that then, like in the video.
Yeah. So if I give you the data, it means you got to watch it and actually plot points off of, like you have to watch the pendulum swing and actually plot points through time. You can do it however.
Okay.
So if we already made our pendulum and did the motion analysis,
If you made your own pendulum, Danny, that is fine. We tried to make it easy for anybody who didn't have a way of doing all that stuff in their house. Even though a pendulum is not a huge ask, I understand that maybe you don't have a protractor or an accurate way of measuring angles, right? So we tried to be accommodating to all. Right. So if you did use your own pendulum, please make sure to include pictures of it and all that stuff in your lab report, right? Here's a good time to talk about this. In general, for lab reports, I really do not want you to put bulleted lists in your materials and methods section. Please do everything as prose, right? Paragraph form. Cody, I do not want engineering notebooks. I want you to type it up using the lab report template that is in LoudCloud. I need one write-up per group. Please include everybody who worked on its name, right? We're working in groups of 2 to 3. Yes. Please include everybody's name on the front cover page, and then I will provide feedback in everybody's LoudCloud Dropbox, so you will be able to know what I took points off for. It's not just going to be one person who gets the feedback. Everybody will get the feedback.
Are we both submitting it? Are the lab group members both submitting it, or 3 people submitting it at the same time, or is it just one person?
I only need one.
Okay.
Okay. And then you just want all the names on it.
Yep.
Okay.
Hey, Dr. D, going back to the example problems.
Hey, Cody, I'm sorry. I can't really hear you.
Oh, sorry. Going back to the example problems, number 6.
Yeah.
There's no notation for any like torques or forces on it.
Example problem number 6, like the sheet that I gave you out.
Yeah, it's just the image of like the propeller engine system.
It sure is. Sure is. Let me take a look real quick. Yeah. Yeah, so just you don't use an applied torque input, just use a motion input of your choosing.
Okay.
All right. All right. You guys have any other questions on this? You guys want to go to the next one? Like I said, the rest of this week is us just we're gonna slam problems. Right. There'll probably be a time trials at some point, just because. Oh, I didn't update. So I updated the track wizard standing in Discord. I don't know if anybody's been in there, but if you use exclamation point TQ points, it will give you an up-to-date real-time results. Right now, we've got life livers and 185.31 as tied for first, and everybody else is in third. right? Everybody's got 8 or 6 points. That's how it's running right now. We'll see how that shakes up later.
Professor, do you have one question?
Homework handwritten, please.
Professor, do you just have one question? For exams, are we going to be receiving something similar to this like example problem set and then just have to compute the equations for it?
For exams, like what format does the exam take? Is that the question, James?
Yes, sir.
All right, it's going to be very similar to the way that the homework is structured. So there will be a little bit of theory that you have to answer, like short answers for, and then you'll have like a couple of problems that you have to do.
Okay, thank you very much.
Can we type out the first 6 questions and then handwrite the other parts, or you want those handwritten?
It's fine. I want
Perfect.
I want all of your problems done so I can see all of your work, right? If you don't include all of your work and you just include an answer, chances are that you are not going to get any partial credit, right? I need to see if you want to maximize the amount of points, like if you're, that's like, you should, everything you write down, just hand it in. Okay. But for the first ones, like the short answers, yeah, you can type those. That's fine. I don't have a problem with that. But you know, the problems definitely you want to show all your work.
And you said there was a lab template in announcements?
A lab report template on my cloud somewhere.
Oh, somewhere. Okay.
It should be in the path. I'm thinking it's in the course materials. Okay. Cool. Hopefully that helps with that last problem helps a little bit with the pendulum lab if you guys are having any questions. How do I grade the homework? Typically, I print it and then I use a pen coding. So what I do is I will grade your entire theory section and then I pick 3 problems at random to grade. I don't know which ones they're going to be until I start because I use a random number generator and it just gives me 3 numbers, and then everybody's homework will be graded according to those 3 problems and you'll get feedback for it. It is not a right or wrong thing, right? If you don't get the right answer, you don't automatically get all the points off, right? I go through and I check all of your work. This class is about the process of solving the problem, right? And so like I've been saying in class, if you mess up the free body diagram, you still have a chance to get everything else correct if you did the right set of equations for the wrong free body diagram, right? So each part builds, right? And if you do all these things in order, like I've been doing them, right? You draw a free body diagram, you write your inputs and outputs, you do your mathematical truths, right? Those things stack as parts, right? And each one builds on the previous part. Now, if you got points off on the previous part, that stinks, but you can still get full points on the next part if you did it correctly with what you did so far. Okay.
And then Dr. Du, just a general question. Are groups limited to 2 or are 3 also acceptable?
2 or 3 people for labs, it's fine.
And then in addition for the lab, you had said you don't want a list of the materials, like listed bullet points.
Yeah, I do not want bullet points. I want everything to be paragraphs. Like,
okay,
right?
thank
It's almost like
you.
journal article-esque, right? We use MATLAB to analyze our data, and from Natick, Massachusetts. Anyway. Cool. Anything else? Any other questions? This was a productive break from doing problems. All right. Oh, there it is. All righty. So, Scott Martin, come on down. You're the next contestant.
Okay.
All right. Well, we got free body diagram, right? So you're gonna have to turn off your background
Oh yeah.
Because the virtual background likes to eat paper.
Cool. So for this one, 2 free body diagrams. This one for the rotation, and then this one for the mass hanging below.
Nice. I like it. It was good. Okay. What about inputs and outputs?
So inputs for the rotational would be the torque, and then output. I meant to put omega actually.
Omega. Is it omega? So what do we want to happen, right? Do we want
we want to lift the block.
right? So is that an angular velocity or linear velocity?
Linear. I did put v, but then I second guessed myself.
It's v. All right. Cool. All right. So I'm gonna draw the free body diagram up here, just so we can all. I'll take a look, right? But yours look good, right? So you're right. We're gonna need 2, right? And this is really the first time that we're seeing a system that has a part that's rotating and a part that's translating, right? So this is a mixed system here, right? So we're gonna have this, right? And we'll say that this has some J. I'm gonna say this is a large R, capital R for the radius. Right? Got my tension coming in. I've got T sub B. I'm going to say that things are going, omega is going that way. And there's some force, right? There's some force hanging off of here. We'll call it F. Connected to that is this mass. And I know it's uncanny. It's like you're looking at the sheet of paper right now, right? That good. My skills of artist. Okay. So we've got this, and I've got some. I'm going to assume that my velocity is positive upward here. Okay. And we were told that there's also gravitational force. Right? The picture itself indicates to us that there is gravity pointing downward, right? So we need to keep it in place, right? And there's no spring, right? If we were modeling a spring, a stiffness in this line, then we would not include the weight, right? Because of what we showed last class. But in this case, we have to include it. It's important to note, right, that C sub T in the diagram, that's a damper, right? Sometimes, depending on what book you look at, some books use C as your damping coefficient and some use B. That's just how it works, right? Is everybody cool with this free body diagram and see how it was generated, and any questions on the free body diagram itself? So, all right, so input, Scott, you said was torque, right?
Yeah.
And what was the output?
The velocity.
Cool. So what do we have for mathematical truths? What do we have there?
I had sum of the forces equals mass times velocity.
Okay. Mass times what?
Velocity.
Is it times velocity?
Sorry, acceleration.
Okay. Which, as hopefully we recognize, that is mass times velocity dot, right? What else we got?
Sum of the torques equals J omega dot.
Okay.
Torque equals force times radius.
Okay.
And then
the damper torque is B omega.
Cool. Awesome. Yep, that looks about right? Now you notice there's no prompt with these, right? I just gave you guys pictures and we're supposed to make models, right? So how do you know if you want it to be a function of velocity or position, right? It doesn't really matter, right? It doesn't really matter. They're equivalent. So in this case, because there's no stiffness, it's easy enough to put everything in terms of omega and make it a first order equation, right? Which is really why we're doing it, right? Because now instead of having a second order equation here, we have a first order equation, right? And the first order equation is often simpler to solve. Right. So did you do the reduction, Scott, or?
Yeah.
All right, so I will stop sharing so you can run us through that and let us know what you did.
Okay. So I did right here for some of the torques for the first one equals torque minus the damper torque minus the force times radius. And then also for the second, or for the mass, the hanging mass, here's the reduction, and the sum of the forces equals force time minus mass times gravity.
Okay, so you don't need the radius there, right? Because it's not a torque on the mass, it's just the force, right? It's not F times R. It should just be that force minus gravity.
Oh, okay, true.
Right.
Yeah.
But otherwise, looks good. And we'll stop there because we've got like 5 minutes left in class. But that was pretty much that was it, right? You could also rewrite the whole thing in terms of like what is the equivalent stiffness, right? But yeah, that's it. Good job. Right. So I will just write it up here just to make sure that everybody's got it too. Thanks, Scott. All right, so we're going to reduce this. If we start with the inertia, right, the rotational side of the J omega dot is equal to my torque minus my damping minus my force times my radius, right? Because that is my torque. We can separate these things out, right? And we'll end up with something like this, right? For the math, for the rotational side, right? So J omega dot plus B omega is equal to the torque minus the torque produced by the hanging mass, right? And for the mass, we'll have M V dot. And what are my forces? Oh, I just got that force minus the weight. Right, and that's that. That's that, right? We could keep going and we could do something similar to what we did before where we combine everything. But for right now in class, like that's really as far as we need to go. The only reason that we would want to combine these is if we wanted a total system-wide transfer function, which we don't know how to do yet. So we're not going to do it. All right. You guys have any questions on this? We doing okay? Next class, we'll start with problem 3, right? The rack and pinion gear. Right. I'm gonna leave this pause for a second and get to the end.
Oh, Dr. D.
Yes.
Just going over what you said previously about the methods and materials, you don't want a bulleted list and that you'd rather have it explained. What's your ideal format for that section?
What do you mean? Just like paragraph telling me what things you used to do the experiment and how you did it. I guess, well, that, how you did it would be, yeah. Right, so for example, pretend like you made the pendulum, right? So cut a length of isochore fishing line to, X inches or meters, whatever you decide to use as units. There was just go over your materials and your methods, I guess, yeah. All right, guys. I got office hours from 3 to 5 today. Stop by. You don't need an appointment or anything. Just hit the link and come on in. I might be a little bit later than 3 just because I teach up till 3. So if there's no meeting, just hang tight. I'll be there. I promise. All right. All right. Other than that,
Thanks, Dr. D.
we're good.
Thank you. Have a good one.
Have a good one, guys.
See you on Thursday.
Have a nice day.
Thanks, Dr. D.
Hey, Professor, what are your office times tomorrow? Is it written in the roster?
Office hours tomorrow are going to be 3 to 5 p.m. Okay.
Thank you.
Basically every day 3 to 5 p.m. except Mondays and Thursdays. Should be, if you go to LoudCloud under the class roster, there's the instructor tab. It should all be listed there. Please let me know if it's not.
Thank you.